Hi, welcome to my channel EasyML. In the previous set of videos, we looked at the theory behind building regression models. In this video, we will see how a regression model can be built on the iris dataset. First, let us install the relevant packages that are a prerequisite to building regression models. I will use the install.packages function to install the relevant packages. So, install.packages stats install.packages dplyr install.packages ml metrics. Well, now let us go through each of these packages. So the stats package has functions that can help build regression models. Second, the dplyr package has functions that can be used for data manipulation. Lastly, the ML metrics package. Well, the ML metrics package has functions that will help evaluate the accuracy of the regression model, which we will be building shortly. Note that I will not be running these lines of code since I have already installed these packages. Now recall, when we performed data exploration in R, I had mentioned that the library function allows us to access the contents of a particular package. So let us invoke the library function to access the functions and the contents of these three packages. So library stats, library dplyr, and then library ML metrics. Done. So I'm going to select and quickly run these three lines of code. Here in the console, you can see that the libraries for these three packages have been successfully loaded now. Now, let us go ahead and load the iris dataset into an object called base_data. So I will create an object called base_data, which is equal to iris. And it is important for you to note that the iris dataset is available by default in R. So I will just execute this line of code here. Now you can see in the environment tab that the object called base_data is created. It has 150 observations and 5 variables. Now let us go ahead and deploy the view function to see the base_data in a tabular format. So I'll use the view function to inspect the base data object. So control enter. Here you can see that a tab has appeared, right, which has the whole data set in rows and columns format, essentially the tabular format. Here you can observe that there are 5 variables, right? We can see sepal length, sepal width, petal length, and petal width, and finally the last variable, species. So let us now inspect this data further. We will use the str or the structure function to inspect the data type of each of these columns or variables. So str base_data, control enter. Here in the console, we can see that sepal length, sepal width, petal length, and petal width are of data type num, essentially stands for numeric, whilst species has the data type of factor. Essentially, factor is R's way of defining a variable as a categorical variable. If you can recall, why do we build regression models? What is the reason or the rationale behind regression models? Well, regression models is built to predict a numeric variable. So here in this data set, we will be predicting the numeric variable petal length. Before building a regression model, let us first select the numeric variables from the base data object. So here in the base data object, you can see that there are 5 columns or 5 variables. The first 4 columns or the first 4 variables are numeric in nature. So I will use the select statement to select these first 4 columns and load it into a new object called myData. So let me go ahead and create object. So myData is equal to select. I'm selecting from base data. What am I selecting? I'm selecting the first 4 columns. So 1, 2, 3, 4, first 4 columns. So and then I just press Control Enter. Here now in the environment tab, you can see that the my data object is successfully created. It is right below the base data object. Now let us again deploy the view function to inspect this my data object. So view my data, control enter. Now the my data tab has appeared. As you can see, here you can see that all the numeric variables have been successfully stored in this object. Now if you can recall from the previous videos, when we were going through the theory behind regression models, I had explained that there are two steps before building a regression model. Step 1 being variable selection and step 2 being splitting of data. Now let us take a look at the first step, which is variable selection. In the previous videos, I had also mentioned that variable selection is a process where we select relevant predictors that can help predict the target or the predicted variable much better. The target or the predicted variable in this case is petal length. How can we select relevant predictors? Well, if you can recall, the correlation matrix is one of the best ways to select predictors. For those of you who need a refresher on correlation and variable selection, please click on the links provided below. Let us now build the correlation matrix to select the appropriate predictors. I will use the core function to build a correlation matrix and store it in an object called CM. CM essentially stands for correlation matrix. CM is equal to core, C-O-R, open brackets, my data, and then control enter. So the correlation matrix has been successfully stored into the object CM, and you can see that the object CM is successfully created. You can see that in the environment tab. Now let me go ahead and see the correlation matrix. So control enter. Here in the console you can see that the correlation matrix has now appeared. Again, if you can recall, I had explained that any correlation above 0.3 or below minus 0.3 is deemed to be significant. And also it's also important for you to remember that when we select variables or predictors, we need to select them in such a manner that they complement the target variable but are not substitutable amongst one another. Now, keeping these two concepts in mind, let us move on and select the relevant predictors. We need to select predictors for the target variable petal length. Let us now go on and see how each variable is correlated with the target variable or the predicted variable petal length. Here we can see that the first variable sepal length has a correlation of 0.87 with the target variable petal length. Let's move on to the next variable, sepal width. Well, sepal width has a correlation of approximately minus 0.43 with petal length. Now the next variable, petal length and petal length have a correlation of 1. Obviously it's correlated with itself, this is but obvious. And finally let's move on to the next variable, petal width. So petal width has a correlation of 0.96 with petal length. So out of all the variables, there are 3 potential variables that can be predictors, that is sepal length, sepal width, and finally petal width. After reviewing the correlation coefficient of each of these variables with petal length, it is safe to conclude that all these 3 variables complement the predicted variable petal length. In other words, all these 3 variables are strongly correlated with petal length. Now, let us go ahead and check whether these 3 variables are substitutes or are substitutable amongst one another. We can say that 2 predictors are substitutes if they are highly correlated with each other. Now, if you observe carefully, you can see that sepal length and petal width have a very high correlation of 0.82, which means that these 2 variables are substitutes. Hence, when I select predictors, I will either select sepal length or petal width. For this example, I have selected the following predictors. I will be selecting petal width and sepal width to predict the numeric variable petal length. Now let us move on to the second step before building a regression model, that is splitting of data. Recall that we split the data into two samples, that is training and testing. The model will be built on the training set, whilst the accuracy of the model will be tested on the testing data set. I will use the sample function to create an object called index, which will in turn be used to split the data into training and testing. So let me first create the index object. Index is equal to sample 2, n row my data, replace is equal to true, probability is equal to C 0.7, 0.3. Let me just quickly execute this command. Now you can see that the index has been successfully created. It is reflected in the environment tab. So now let us go ahead and explore. Let us go ahead and see what I just did here. What is the sample function? Let's go ahead and inspect this sample function. So first, inside the sample function, you type how many samples you want. So here I wanted 2 samples, that is training and testing. Hence I have typed 2. So I want to select these 2 samples from the number of rows in my data, right? Hence n row my data. It is also important for you to note that the my data object has 150 rows or 150 observations. Here I will be taking the samples with replacement. Hence I have written replace is equal to true. This is done to ensure that at each stage of selection, each unit has an equal chance of being selected. This is just done to ensure random sampling. And finally, the split. So when I explained data splitting, when we were going through the theory behind regression models, I had explained that the analysts choose to split data in various compositions, like 50-50, 60-40, 75-25, etc. Here I have chosen a 70-30 split. As you can see here, 0.7 and 0.3. This essentially means that 70% of the observations in the data will be assigned to the training set and 30% of the observations in the data will be assigned to the testing set. Now let us take a closer look at the index object. Index, control, enter. Here in the console, you can see that there are 150 values, same as the number of observations in the my data object. Here, all the ones represent those observations that will be assigned to the training set, and all the twos represent those observations that will be assigned to the testing set. Now let us deploy the table function on the index object to explore this further. Table, index, control, enter. Well, here you can see that 115 observations are in the training set, that is index equal to 1, and 35 observations are in the testing set, that is index equal to 2. So if I add 115 and 35, I get 150. 150. So that is what we wanted, right? We wanted to split 150 observations in such a manner that 70% of the data is in the training set and 30% of the data is in the testing set. Now let us go ahead and build the training and testing data. I will create 2 objects, namely training and testing. So training is equal to my data, where index is equal to 1, and testing is equal to my data, where index is equal to 2. Let me just quickly select and run these 2 lines of code right here. So from all the observations in the my data object, I have selected those observations whose index is equal to 1 to get the training dataset. Similarly, from all the observations in the my data object, I have selected those observations with index is equal to 2 to get or obtain the testing dataset. You can also observe in the environment tab that the objects training and testing have been successfully created. Now, since we have completed steps 1 and 2, that is variable selection and splitting of data, let us move on to build the regression model to predict petal length. I will now load the regression model into an object called RM. Naturally, RM stands for regression model. I will use the lm function from the stats package to build the regression model. So let us go ahead. So I'll create an object called RM, and I will use the LM function where petal dot length length tilde petal dot width plus sepal dot width comma data is equal to training, and then control enter. Here's the RM object is successfully created. You can see that in the environment tab, and this is as simple as that. We have built the regression model now. So let us go ahead and inspect what I just did here. Let us go ahead and inspect the LM function. So first in the LM function, I wrote my predicted variable. Since we are predicting petal length, that is what I've written first. That is followed by the tilde sign here. Tilde essentially means, okay, I'm predicting petal length with the help of what? What are the predictors? So it means followed by what? So the predicted variable is followed by the predictors, and that is depicted by the tilde sign. So here my predictors are petal width and sepal width, as I've highlighted here. And I've chosen these predictors from the correlation matrix, which we just saw a few steps before. So finally, the data set on which I'm building this model is obviously the training data. Therefore, data is equal to training. Let us now inspect the regression model that we have just built. Recall, there are two ways to evaluate the regression model. One is to check the model efficiency, and the other is to check for model accuracy. Let us first evaluate the model efficiency. So for that, we will use the summary function. So summary RM control enter. Well, if you can recall, there are three things that will help us evaluate model efficiency. First is cause and effect. Second is to assess the quality of the predictors. And third is the R-square value. For those of you who need a refresher on these three concepts, please click on the link provided below. Now, let us move to the first concept, that is cause and effect. Here we can see that the variable or the predictor petal width has a coefficient or an estimate of 2.14. Well, this essentially implies that if petal width changes by 1 centimeter, then petal length will change by 2.14 centimeters. Similarly, let us take a look at the next variable, sepal width. So sepal width has a coefficient or an estimate of minus 0.36. So this essentially means that if sepal width changes by 1 centimeter, then petal length will change by minus 0.36 centimeters. So the estimate here, the estimate essentially captures the cause and effect relationship between the predictors and the predicted variable. Now, let us go ahead and assess the quality of the predictors. So, petal width is my first predictor. This has a star rating of 3 stars. Sepal width is my second predictor. This has a star rating of 2 stars. Now, if you can see here, there's something called significance codes, and significance codes has a star rating of 3, 2 star, 1 star, and so on. So essentially 3 star means it's an excellent predictor. It's the best that you can get, right? So more the number of stars, better the predictor is. So the petal width is an excellent predictor. So it has got 3 stars. Sepal width is a very good predictor. Hence it has got 2 stars. Now let us take a look at the last concept, that is the R-square value. Here, the R-square value. So the R-square value is roughly 93%. Which in this case implies that 93% of the variation in petal length is explained by petal width and sepal width, which is again pretty high and which is actually extremely good. Now, let us go ahead and evaluate the model accuracy. We will use the predict function to get the predicted values of petal length. I will be storing the predicted values of petal length in an object called petal length pred. So let me first create the petal length pred. Petal length underscore pred is equal to, I will be using the predict function now. Predict, 1 second. So predict function say RM and then comma testing. So just give me a minute. It's just a minute here, please. Yeah, so control enter. So let us now break down the predict function. First, in the predict function, I will feed the regression model. So the regression model that is built on the training data set. Then I pass the testing data set, that is right here, testing. So what does the predict function actually do? Well, so it uses the model built on the training data set to predict petal length values in the testing data set. So I will now add the predicted values to the testing data set using the dollar symbol. So testing dollar petal length length pred is equal to petal length pred, and then control enter. Now let us take a look at the testing data set, right? So I'll use the view function for that. View testing, control enter. Now you see that the testing data set has appeared as a tab, right? So here in the testing data, I have both the actual values of petal length and the predicted values of petal length. So for the first observation in the testing data set, the actual value of the petal length, if you observe, is 1.3. But the model has predicted the value of the petal length for this observation to be around 1.6. So in this testing data set, we will compare the predicted and the actual values to check for prediction accuracy. One of the best ways to evaluate prediction accuracy is via a metric called MAPE, that is mean absolute percentage error. For those of you who need a refresher as to why that is the best metric, please click on the link provided below. Now let us calculate the MAPE using the MAPE function. And I will be storing the mean absolute percentage error in an object called error. So I will just go ahead and say error is equal to, I'm going to use the MAPE function. So from the testing data set, I will be first selecting all my predicted petal length values and then comparing it from the testing data set. I will be comparing it with the actual petal length values, and the MAPE function will help calculate the error or the difference between the predicted and the actual values. Let me just quickly execute this command right here. One second, sorry. Oh, sorry. Control enter. Here you can see that the error has now been calculated. So again, let me just reiterate, let me break down the MAPE function. The MAPE is calculated between the predicted and the actual values, right? So that is exactly what is fed into the function. First, I have fed the predicted petal length values from the testing data. See, this is the predicted petal length values from the testing data. Then I have fed the actual petal length values from the testing data. And the percentage difference is the error which is stored in this object called error. It's as simple as that. Now let us take a look at the error. So error, control enter. Here I can see that the error is around 13%. So obviously the accuracy is 1 minus the error term. So my accuracy is going to be 1 minus error, error, which is control enter, which is about 86%. Therefore, conclusively, the accuracy of the regression model built to predict petal length using the input variables petal width and sepal width is around 86%, which is actually extremely good and very high. In the next video, we will look at how we can summarize this whole workflow when it comes to building regression models. Thank you and stay tuned.